some amplitude that's any function of p whatsoever, this amplitude to get from 1 to 2 is not, and in fact it cannot be, 0 when 2 is outside of the light cone of 1. And that's a shock to anybody that doesn't know that if you started a series of waves out, they can't be confined in the light cone if the energies are always positive. That is a very important thing, and it therefore must be the result of some sort of theorem. And so I made up a mathematical theorem, the proof of which I don't know, but I'm sure it's right in this application. In this application. That is, if we put together a function only with positive frequencies, defined this way, the integral only over positive omega, with any weights whatsoever, to produce a function of f of t, then that function cannot be 0 for a finite interval of time. You see, ordinarily you're a little bit surprised there, because you know that you can take a piecewise function at 0 over a range in Fourier and analyze it, but then you'll get both positive and negative frequencies, and I'm insisting there only be positive frequencies. I got half as much data to work with, and I have two functions, the real part and the imaginary part of f, both be 0. Now, it may be that some clever mathematician can cook up some way that could almost happen with some kind of a e to the 1 over x or some terror, but I want it to be 0 over an interval of time, you see, inside the light cone. And then if I change x, which changes all the phases and everything else, is still 0. I don't think you can make it work 0 outside the light cone. So the point is, it's definitely so that this function cannot be 0 outside the light cone. In other words, there's an amplitude for particles apparently to propagate faster than the speed of light, and no arrangement of superposition can get around that. Therefore, if time t2 is later than t1, we have an amplitude to have a connection like this in which a particle goes across faster than the speed of light. But because of the principles of relativistic invariance, there are axes. If these are separated by a space-like interval, there's a speed at which time t2 appears before time t1. Now, we're not changing the formula. We have this same process, but we're going to look at it from this other coordinate system, and what do we see? We see a process by which at 2, first thing that happens, see time is this way now, first thing that happens is a green thing and a black one come out, and later on the green one annihilates with the black one. To draw it turned a little bit, it'll look like this figure, which is a new process. This green line before used to go forwards, and now it's going backwards. So what we have to allow, and we have to include it in order to get any type of relativistic invariance at all, is a section of paths running backwards. The possibility of a production of a pair and an annihilation by a disturbance. In other words, there must be antiparticles. In fact, because of this difference of the coordinate systems in two different speeds, so that which is ahead of which depends upon which way you look at it, we can say this, that one man's virtual particle is another man's virtual antiparticle. Therefore, first of all, antiparticles in pair production must exist, and second, antiparticles' behavior is completely determined by particle behavior. There's absolutely no freedom. You know what the particle does, you know what the antiparticle does. How? You just look at it from the other end. Because one follows one way and the other way. To summarize this very crudely, and I'll do this very much more accurately and fancy later, if we reversed everything, we would reverse the sign of x, y, z, and t, then we should be using an antiparticle. I call C conjugate, charge conjugate, or whatever it is, the difference between a particle and an antiparticle. And this change of the sign of time and the three directions of space. Let P represent what's called the parity operator, which changes the three directions of space. So PT is C, right? But we're finished. We understand why they're antiparticles, and we understand that wonderful theorem that CPT leaves everything unchanged. Okay? And therefore, since I've already done what I said I would explain, why they're antiparticles, I'm finished with the lecture. But in order for that's all there is to it. It has to be that they're antiparticles in order to get relativity. In order to determine the sizes of the amplitudes, this didn't talk very much about the sizes. There are lots of relationships among the sizes of the amplitudes, and this leads us in a new direction in which we're going to get a clue about the connection of spin and statistics, because the antiparticles are making new particles, and we'll see how it works. And the key to that is another proposition, and is that the total probability, I don't never can spell probability right because I haven't got the patience, of all possible events always has to add up to 100%. But let us analyze this in the lowest order. Suppose there's a potential disturbance A. We already talked about how a particle coming in at momentum 1 can be deflected to some momentum P with some amplitude A. The absolute square of that is the probability of deflecting a particle to momentum P. Actually, I include in A the wave function coming up if you look back at it. Now, we can also calculate the probability of not doing anything. That is, to leave the object, the original particle, where it was before. And this is, the amplitude is 1 plus alpha, where alpha was that diagram that we made before. And the absolute square is this thing plus that thing. It's complex conjugate, I mean, because 1 plus alpha absolute square is 1 plus alpha star plus higher order. And so there's a definite connection in size and sign that has to be right so that these two terms that added together will cancel this. In other words, that these two add up to a negative amount. I left out a lot of i's and things like that in here. We'll always put them back if you want them, but the point is these two things have to be this, that the probability of not doing anything is reduced from 1 by the same amount as the probability of doing something is increased. All right? So that the sum of doing something and doing nothing is still 1. So that connects this size and sign and everything to that. We can prove this way that B has to be A star, but I don't need to bother you with that, so I won't bother you with that. Okay. Now, that was the non-relativistic case where we only had particles. Now we have a problem. We have added a new diagram, a new possibility. We not only have the 1 for the particle to go straight through, but the probability to do nothing is 1 plus twice the real part of this picture, which I'll call I, and twice the real part of this pair production picture, which I'll call Zwei. All right? Now, it's easy to check, very simple, that twice the real part of this one cancels the probability to make a transition from 0 to P. That works. That's just the same as it did before. What have we done, however, is we've added another piece, and so we have to find out what it is that this absolute square is correcting for. All right? Well, if you work out see, the size of this and that are completely determined. As we just pointed out several times, a particle and antiparticle are absolutely related. So the size of this is completely determined. And this thing, you can work out, I'm talking about spin 0 particles now, it cancels the probability to make a pair with the electrons in O and the antiparticle has momentum P. That is to say, this is the negative of this probability. Now, what does that mean? You see, that's easy. You say these are all the probabilities of producing pairs, but it isn't really, because you could produce pairs with any moment for the electron. And that's all canceled by something else, which is in a vacuum that we can come back to. But here is a special case in which we produce a pair with the electron in the same state as O. We have somehow, in order to make this all work, because this is a negative contribution, to say, in order to make it consistent, it has to come out that the probability of producing a pair with an electron in O is enhanced when there's an electron present in O. And that enhancement is what's being canceled. And that's the principle of Bose statistics that makes the lasers work. That if there's a particle in the given state, the probability of producing a new particle is increased. It's doubled, in fact. And this extra 1, 2 is 1 and 1. The extra 1 is the thing that's canceled by this, and that's how it balances. And so we can get a clue as to why the Bose statistics are the statistics for spin 0. All right? Now let me just outline it again. We've added an extra diagram, told us about a new process called pair production. We discover when we try to check the